learn the four fundamental subspaces. And as we know from the previous things that the rank of the matrix is equal to, at the max, the rank of the matrix can be equal to n, and in case of the m into n kind of matrices, the rank is equal to the number of pivot variables, and we can have r is equal to m is equal to n for the square matrix, and we can obtain the left, right, and the two-sided inverses for the matrix A. Now let's learn the four fundamental subspaces. What all are these four fundamental subspaces? These four fundamental subspaces are the column space, that is C of A, the null space, that is N of A, then row space of A, that is C of AT, row space of A, that is nothing but the column space of AT, that is C of AT, and the left null space of A. The left null space, we'll see that one later. The left null space of A is nothing but A transpose, and it contains all the vectors y such that A transpose of y or y transpose of A is equal to 0. So in brief, we can say that it is the null matrix of A transpose matrix. So let's learn them in detail with these. So the four fundamental subspaces we have listed, and let's take up an example to understand what this column space, null space, row space, and null space, left null space are these. So let's take an example that A, our A is equal to U and is equal to the reduced matrix R also, which is this one, 1, 0, 0 and 0, 0, 0. Now here it's clear that 1, 0, 0 is having a non-zero row, and second one is a row of zeros. When we have the row of zeros, it is not contributing anything. Now let's write the column space of this. The column space of this one, only this first column, we have 3 columns here. Out of them, the first one is contributing to the value of the matrix, but the rest are no. So 1, 0 is the column space of this matrix, and even all the multiples of this 1, 0. If it is getting multiplied by 2, 2, 0. If it is getting multiplied by minus 1, then minus 1, 0. If it is getting multiplied by minus 2, 0, minus 2, 0. These all are the column spaces, but they all are being obtained by multiplying this with a value, with a constant. So 1, 0 is the column space. Then the next point is the row space. The row space of this matrix is nothing but we have 2 rows, but the first one is having a non-zero rows, and second one is having zeros. So the row space is the line through 1, 0, 0 transpose, or it is 1, 0, 0. So row is nothing but 1, 0, 0. It is R3. We can write it in the column space. Otherwise, column way, in the row way, if we write, let's write the transpose. It is 1, 0, 0. I hope it's clear, because second is not contributing anything. Then next is regarding the null space. Then what is a null space? We are familiar with Ax is equal to 0 solution. Null space is nothing but the space which gives when this A is multiplied by what matrix, by what constant, Ax is equal to 0, that kind of a thing. By what, if I multiply this one, a list of unknowns, certainly 3 are 3 column vector. By what values if I multiply, I get zeros. So that is contributing, or that gives me the null matrix, the null space, sorry. The null space, to obtain that one, let's see, it is 1, 0, 0, So it's as 1, 0, 0. So 1, 0, 0, when it is multiplied with x1, let's say x1, x2, x3, then if it is getting multiplied by what? I'll get zeros. Then I have to make this first element as 0, so I don't have to take my x1 as 1. If I take, then 1 into 1 plus 0 into whatever this element will give us non-zero result. So the first has to be 0, the next can be anything because these rest elements are zeros. So if I take up 0, 1, 0 as the null space, then 0 into 1 would be 0 plus 0 into 1, 0 plus 0 into 0. So I'll get a 0. Similarly, this way, I should get only 2 zeros here. So when these are multiplied, this multiplied by this first, this multiplied this. So it is not that. This we don't get, only 2. So I hope the null space is also understood. Then what is the transpose? The left transpose, well, what is the left null space? The left null space is to be obtained. So null space is nothing but it is 0, 1, 0 or 0, 0, 1 pertaining to this matrix. So which makes this R into these values as 0. Then the left null space is A transpose. It is nothing but null matrix corresponding to the A transpose matrix. So first we'll obtain what is A transpose. A transpose is the transpose of this matrix. Let's take this. And when we multiply this A transpose with what values? If this A transpose is getting multiplied with what values? I'll get zeros. So we should get, so the number of these are to be 3. So we'll get 3. So when we take now this first element, now we know the multiplication, this column should have first element as 0, second could be anything. So let's take it as 1. Now if we take 0 and 1, 0, 1 as the combination, when it is multiplied with this, we'll get, so 0, 1, 1 into 0, 0, and 0 into 1, 0. So first row becomes 0 and these also. So 0, 1 is the left null space. So left null space in the sense the null space of a transpose matrix. So let's see the same things with respect to the matrix A. As we know this matrix A, we have solved Ax is equal to B as well as Ax is equal to 0, the special as well as particular solutions. So we are familiar with this solutions. Then for this A, we have obtained U also, we know by row operations. So we have performed some row operations and obtained this U matrix. So let's learn these four subspaces with respect to these. The row space of A. What is row space of A? The row space of A is nothing but this first one, second and third. We can write the row space of A as like, we can write it as just, it is the first column, the first row is this one. It is 1, 3, 3, 2. We can write. So it is 1, 3, 3, 2. Then next one is 2, 9. We can write it as it's 2, 6, 9, 7. And third one is -1, -3, 3, and 4. So this is nothing but the row space of A. So row space of A is this one. So the third row, now To understand this, the first, when we obtain U from A, the first and second rows contribute, they are non-zero rows, but the third one has gone to zero and getting the echelon matrix. So we can say that the first and the second rows are the basis of this matrix. So here the first and third one are the basis of this matrix. So similarly, these are from the pivots. We obtain that there is a pivot element in the first as well as in the second row. So we can say that these two are the basis of our matrix A. And the how many number of bases are there? 1 and 2. Number of rows are 2. So number of bases are 2. And this is not contributing anything. So the rank of the matrix is 2 because 2 bases are there and 2 non-zero rows are there. So it is the rank of the matrix is 2. So as rank is 2, the dimension of the matrix is nothing but the rank of the matrix. So it is R. Now generally we can say R is the rank of the matrix. So dimension is always equal to the rank of the matrix. Now for this matrix, rank is equal to 2, as we obtained with the column operations also. And with this, and even we know that after solving, when we obtain R also, we know that this C1 and C3 are independent columns, and these second and fourth are the combinations of the first and 3. So even by judging in this way, we can say that there are 2 independent columns here. So the rank of this matrix is 2 and the number of pivots is also equal to 2. So the row space of A has the same dimension R as the row space of U. The row space of this as well as the A are going to be same. The rank of the matrix or the row space will not change the rank of the matrix, even though how many row operations, whatever may be the row operations performed, the rank of the matrix will not be altered. So rank of U and A are equal. So that is the meaning. Then the next one is null space of A. We have solved this matrix A for obtaining the null space, that is Ux is equal to 0. And we know that solution we have obtained in this way. So that matrix was there. Here U, V, W and Y were there. We have written the equations of them and went for solving by considering the first. So for the free variables, we have to take the values. So here V and Y are free variables. First we take V as 1. So the values will be this and Y is 0 here. And when we reverse, when our V is 0 and Y is 1, the values taken by those equations would be this. And I hope you know what is a null matrix. Ax is equal to 0. This null matrix is also referred as the kernel, and the null space has a dimension n minus r. So n is the number of columns, r is the rank of the matrix. Always the dimension of null matrix, the null space, is n minus r. So here for A, n is 4 and r is 2. So the null space is 2. We can have 2 null spaces. Then the column space of A. The column space of A is nothing but the list of columns. And we know that these columns are not, these all are not independent. Only first and 3 are independent, and these 2 are the multiples. The second one is the multiple of first, and the fourth one is the linear combination of 1 and 3. So the basis of this column space, here the basis of this column space are only 1 and 2. So the first and third columns of U are the basis for its column space. Even we can refer this U. The first and third are the basis which contribute to the pivot elements. The pivot columns of A are the basis of its column space. So we are familiar with this. First and three are the pivot columns. The dimension of column space C of A equals the rank, of course, and which also equals the dimension of row space. So even by considering the number of rows, non-zero rows, we may go for obtaining the rank, or we may do it by using the pivot elements. So the rank is going to be the same. So the rank obtained by row operations or by column operations is going to be the same. So R is equal to 2 with this A. And if we are solving this example wherein the 4 into 6 matrix is there, here the number of pivot elements are 3. So we'll be having the rank of this matrix as 3. And as there is a row of zeros here, and n is equal to, we'll be having n as 6 here, m is 4 and n is 6. The pivot variables are 3. The number of free variables are also 3. It should be 3. So the rank of the matrix is 3. So column 1, column 4 and column 6 are linearly independent, and when we take, as they are linearly independent, the value of C1, C2 and C3 have to be 0, because if they are other than 0, we can't say they are linearly independent. Then the left null space A, that is null space of A transpose. If A is M into N matrix, then A transpose is N into M. The null space is of R raised to M. So Y has M components. Y transpose of A is also equal to 0. So we may write it as A transpose of Y or Y transpose of A. It works out to be 0. So as we are writing Y transpose, let's write in place of columns, we'll write it as a row, and A is a transpose. A is NA as it is, will give a zeros. Will give a row of zeros. The number of pivot variables plus the number of free variables must match. If the number of pivot variables are 2, the dimension is of the null is 2, the number of columns have to be 4. So the same it is, the number of columns, the dimension of C of A is nothing but 3 here. Dimension of N of A is 3, the number of columns is 6 for this example, and for A it would be 2 plus 2, which is equal to 4. Now let's take an example to understand this. Now let's take A is equal to 1, 3, 2, 6. It is a square matrix. Now as we can see, the second column is the multiple of the first one. If I multiply this by 2, I'll get the second column. So the rank of this matrix is 1. As C column 2 is 2 times column of 1. And N minus R, number of columns is 2. R is 1, so it is 1. The column space contains all the multiples of 1, 3, because this is the basis. The column basis, this one, or it is the pivot column, we can say. So the column space contains all the multiples of 1, 3, that is C1. As C3 is 2 times the C1, and it contributes nothing. Because when we obtain U from this, we'll get a row of zeros. Then null space. an A is obtained by Ax is equal to 0 method. Let's write Ux is equal to 0. And to obtain U, let's perform the second row as. So we change the second row as the second row minus 3 times the first row. So when we operate that, so 3 minus 3 of 1. So gives 0 and second one. Now R2. The next R2 will be 6 minus 3 times the R1. So which is 0. So we'll get 0. And as per the rules, it is our pure element and pure column, and it is a free column. So when we take x1 is a pure variable, x2 is a free variable. And when we take x1 as 1, x1 is a pure variable, x2 is a free. When I take x2 as 1, then I'll get x2 as minus 2. So null space of the given A is minus 2, 1. And even all the multiples of this minus 2, 1. I mean, if it is getting multiplied by 2, then minus 4, minus 4, 2. So likewise, all those will be the null spaces. Then row space. Here, row space means 1, 2. Row space contains all multiples of 1, 2. 1, 2 written in a column space. Then the left null space contains what? How to find it? The left null space is nothing but the null space of A transpose. So let's find the transpose of the given A. It is 1, 2, 3, 6. So let's write it as the A is written as now 1, 2 horizontally 3, 6. Now let's write it vertically 1, 2, 3, 6. Then with what if I do the multiplication? I'll get 0. So if these two are multiplied, so for that let's obtain again U. And when I multiply, to obtain this, I need to cancel this element. So to cancel this element, the operation has to be, the next R2 would be R2 minus 2 times R1. So when I do that, I'll get this matrix and y1, y2. So I'll get the equation as y1 plus 3y2 is equal to 0. Here, as we know, y1 is a pure variable and y2 is a free variable. So when y2 is given a value 1, y1 equals minus 3. So null space of A transpose is minus 3, 1. Now, even a diagrammatic representation is done for all these fundamental subspaces. So let's see how it is done. So a row space and null space of A. The first diagram shows the row space and null space of A. The row space is 1, 2. The row space is 1, 2. Let's represent 1, 2. 1, let's x and y be those axes. And we know the dimension is 1. The dimension of this matrix is equal to rank of the matrix. The rank is 1, dimension is 1. Means we'll be representing them in the form of lines. Now here the representation would be for these all points. The representation is in the form of lines because dimension is single. So a row space is 1, 2. So let's represent 1 and 2. So it is our point 1, 2. It represents row space. Row space is represented by XR. And we'll draw a line joining the origin and this XR. So let's take a scale and draw this line. Now similarly, it is the null space. The null space is minus 2, 1. The null space of A is minus 2, 1. So let's represent minus 2, 1. Minus 2, the null space of A. The null space of A is minus 2 and 1. So to represent this one, we take it as minus 2, 1, minus 2, 1 is this line. So when we take a line joining 0 and minus 2, 1. So minus 2 on this side, left side, and 1. So if we join this line, it will run in this way. And when we project these two lines parallelly, if we take a parallel line to XR on this and a parallel line of XN, and when we join them, we get X, and that X is equal to XR plus XN. So similarly, we can go for the projection of the column space and left null space. So the column space is given by, the column space is 1, 3. The column space, as we know it as 1, 3. The column space is 1, 3. So we can go for writing 1 and 3 this point. It is a line joining this 1, 3 to origin and extend it on either side will give all the multiples of that column space. All the values of that column space will be lying on that line, and the left null space, is the null space of the transpose matrix. The null space of transpose matrix is minus 3, 1. So minus 3 below, minus 3, 1, 2, 3, and 1, this line. And on this, drop the column space, and how this X are related. If we want, then we can go for the projections. So this will be regarding the fundamental subspaces.